Yes, welcome to our lesson 3. We are still introducing electrochemistry. In this lesson 3, we want to look at a term called electrolytic conductivity. Electrolytic conductivity. Now, like solid conductors, even electrolytes obey properties of conductors, which states that when electricity is passing through these electrolytes, the resistance faced by the flow of current is directly proportional to the length of the electrodes and inversely proportional to their cross-sectional area. This is a property of conductors which is also obeyed by electrolytes, that the resistance to the flow of current is directly proportional. The resistance, now my resistance is R, measured in ohms, is directly proportional to the length of a conductor. Now in this case it would be length between electrodes, because in this case we are going to look at an electrolyte where we have immersed electrodes are the ones conducting or allowing the movement of electrons and hence current. So we are saying the resistance R is directly proportional to the length between electrodes and inversely proportional to the cross-section area, of each electrode. Distance between the electrodes is L. If this was a conductor, still we would say the same thing. The resistance to the flow of current on this conductor is directly proportional to the length of the conductor, but inversely proportional to the cross-sectional area. Similarly, for electrolytes conducting electricity, if placed in a beaker and 2 electrodes immersed in this beaker, separated by a distance L, this electrolyte is within this beaker here. Now, this is what we are calling the cross-sectional area. Resistance as a property of conductors, or a property obeyed by many conductors. Resistance is directly proportional to the length, but inversely proportional to the cross-sectional area. This is true for metallic conductors and for electrolytes. Now, we can use this relationship to generate what we call electrolytic conductivity. Now, in this case, if we introduce a constant, R will equal to, the constant for this relationship is called resistivity, represented by this letter, a Greek letter. So this constant L over A, and where this letter rho equals resistivity. Letter rho is resistivity. Now, electrolytic conductivity, electrolytic conductivity represented, electrolytic conductivity represented by a Greek letter kappa is normally equal to the reciprocal of resistivity, meaning it is 1 over rho, like that. And from here we get the definition of electrolytic conductivity. Definition of electrolytic conductivity. We normally say that this is the reciprocal of resistivity at a given temperature. Temperature is one of those factors that would affect conductivity. Now, if this is true, then we can get a relationship between electrolytic conductivity and other variables in the expression. If that is true, then we shall go here and make conductivity the subject, or the reciprocal of resistivity the subject. From this expression, if we make the reciprocal of resistivity the subject, what shall we have? From R is equal to resistivity times L over A. So we want to make 1 over resistivity, which is K, the subject. In that case, we shall first make this the subject, resistivity. So resistivity will equal to R times area over length. And therefore, 1 over rho, which we are calling conductivity, represented by letter K, is equal, the inverse of this should equal to 1 over R times length over A. And therefore we can always say that electroconductivity or electrolytic conductivity K can be given by the formula 1 over R times length over area. 1 over R times length over area, where 1 over R is called conductance. And L over A is called the cell constant. L over A is called the cell constant. Therefore, someone can say that electrolytic conductivity is actually conductance times cell constant. Now, when the length between the electrodes is 1 unit, for example, we are saying when length is unit means 1 meter or 1 centimeter, and area is also unit, which would mean 1 meter squared or 1 centimeter squared. Then K will equal to 1 over R. In that case, conductivity is equal to conductancy. And from that point, we can get another definition and another name of conductancy, or electrolytic conductivity. Electrolytic conductivity is sometimes called specific conductancy, also called specific conductancy, and is also defined as the conductancy of an electrolyte. The conductancy, we are saying the conductancy, it can only be equal to conductancy of an electrolyte when the length is unit and the cross-section area is also unit. So we are going to say conductancy of a solution of an electrolyte, conductancy of a solution of an electrolyte placed between two parallel. Normally the electrodes must be parallel. Two parallel electrodes placed between two parallel electrodes that are a unit distance apart. Unit distance apart means 1 meter or 1 centimeter apart, and each of unit cross-section area. Unit cross-section area means 1 meter squared or 1 centimeter squared at a given temperature. At a given temperature. So if we don't want to define electrolytic conductivity as the reciprocal of resistivity at a given temperature, we can also define it as the conductancy of a solution of an electrolyte placed between two parallel electrodes that are a unit distance apart, and each has a cross-section area of unit or unit cross-section area, which means 1 meter squared or centimeter squared at a given temperature. And we said it can only be conductancy if the length is unit and the area is also unit, and sometimes called specific conductancy. So now, this expression obtained here can be used to make a few calculations concerning conductivity. But before you make a few calculations, it would be very important that we know the units of conductivity. If K, this is the symbol for electrolytic conductivity, is equal to 1 over R, which we are calling conductancy, times length over A, called the cell constant. Then by substituting the standard units of each of the variables here, we can get the units of K. Now, R is measured in ohms, sometimes just written the symbol of an ohm. Length could be measured in meters or centimeters, and area can be measured in meters squared or centimeters squared. So by substituting in the expression above, let's first consider centimeters. In terms of centimeters, K will equal to 1 over ohm times length centimeter and area centimeter squared. The units have to be the same here. And then this will give us the units of K as this, and that will give us per ohm. And then when we are dividing indices of the same base, then we subtract the powers, and this will give us a centimeter down, which will become per centimeter. Similarly, if the units were in meters, also K can be per ohm per meter if we were using meters. Now, per ohm has a modern unit called Siemens. This one, Siemens. So you can find the K as S per centimeter, or you can find the K as S per meter. These are all units of electrolytic conductivity. Sometimes we can even write the word and say K is per ohm per centimeter. We can as well say per ohm per meter. So any of these units could be used to represent units of electrolytic conductivity. When it comes to calculations, it is very important to know the units of electrolytic conductivity. And so you will either find units in the modern units where we are putting the S, or you can find the word per ohm or the symbol per ohm. And that can be used in a few calculations. For example, we could have a question like this. Example, a solution of an electrolyte of concentration 0.02 molar has a resistance of 0.357. A solution of concentration 0.02 molar has a resistance of 0.357 ohms, 75 ohms, in a cell with a cell constant. In a cell with a cell constant 1.5 per meter. Cell with cell constant 1.5 per meter. Calculate the electrolytic conductivity of the cell. Calculate the electrolytic conductivity of the cell. calculate the electrolytic conductivity of the cell. Now, for any calculation where the formula is known, then the first thing that we normally do is to state the formula. So here we would now say that electrolytic conductivity K is equal to 1 over R times L over A. Once the formula is stated, then you substitute correctly. So we shall be in the next lesson starting with the substitution here and then get the answer, and also look at other examples in the same line, and we see how we can make calculations concerning electrolytic conductivity. Please don't miss, follow our channel and view our lessons. Thank you for watching.